Hi everyone. Thanks for showing up for this talk. My name is Sri, and happy to be here. My background is in data science, AI, and machine learning, and some software engineering in different domains: media and entertainment, finance, marketing analytics, and even culinary. And this describes my foray more into the cybersecurity side of things. Because I feel that cybersecurity has an interesting interplay with data science. On the one hand, cybersecurity basically has different techniques such as fuzzing, where you can look into using different inputs with softwares in order to find bugs, errors, or other flaws. And on the other part, so you can basically use that in order to improve the security and the safety of AI. On the other hand, you can use tools from data science, optimization, statistical analysis to make that fuzzing process more efficient, because this is really, the exploration space is potentially huge. So I find this very exciting. So maybe just by show of hands, I just wanted to know, who here has background in cybersecurity? Okay, great. Not a lot of people, and in particular AI security? Okay, so let me get started. Let's see if this, I guess we'll have to resort to this great technology. So the agenda for what I'm going to do today is I'm going to go over some vulnerabilities of AI applications. Then I'm going to talk about AI red teams, what they do, what are their primary roles, and some examples for some activities that they do. Then I'm going to talk about certain workflows for vulnerability discovery, and then I'm going to give one example for a methodology, in particular, evidence-based uncertainty approach to make that vulnerability discovery more efficient. So I'll start with LLMs, some examples of LLMs in the wild. Not that these examples are, not that there are lack of such examples. So one of the examples is New York City last year released a chatbot, and this chatbot, the purpose of this chatbot is to give information for residents of New York City, things like information about school or local regulation and laws, pertaining to businesses and so on. So someone managed to interact with this chatbot and managed to get some advice about how to steal tips from their employees. So that's clearly unlawful things that a chatbot can recommend. Some other more recent LLM examples in the wild. On the right-hand side, we have the Chicago Sun-Times. They basically outsourced some of their content generation to a third party. Apparently, that third party used Gen AI, and the content had to do with some reading list, right? So they referred a lot of books that don't exist or fake, and basically the Chicago Sun-Times went with that, published that, and it was a big reputational damage. The CEO ended up apologizing for that mishap. And on the left-hand side, something more recent from the last few weeks about The Economist, about libelous chatbots, where chatbots actually invent lies about real-world people, and that really creates a huge headache for legal teams in companies. So if you want to become an AI lawyer, that's a great career in the space. So that's just a few examples to illustrate some of the vulnerabilities in LLM-powered applications. So turns out there is a project called OWASP. It's basically a collaboration of companies, small and large, that in cybersecurity. Oops. In cybersecurity. And they also do some work in the context of AI and LLM applications. So
football data and analytics at the NFL League office. I have been there for about.
I don't know what's that thing. So basically, they have identified a list of the top 10 vulnerabilities, and on the right-hand side, we can see some of them. One of them is prompt injection that comes in two flavors. One flavor is the direct prompt injection, and we're going to see about that a little bit later in the presentation. Another one is indirect one, so you can basically inject some instruction into different types of content, and its instruction can be something like forget everything that I have said so far in the prompt or in the data that I have attached, or give me some, give me the password of the system administrator, give me a prompt, give me your system prompt, or, even can do some malicious things beyond just like data leakage type of thing. The other thing I'm going to point out here is number 3, LLM supply chain that people should be mindful of. When typically people who write, chatbots and other LLM-powered applications, what happens is that they use multiple open source libraries to do additional things like charting, like data processing and things like that. So some of the software that they may use is open source, and it could be deprecated or even could be, offered by some bad actors that have some, backtrap doors and other type of things, malicious code that expose the application that the application can be compromised. And lastly, number 5, that I'll mention briefly here, the improper output handling. Typically, when you have LLMs, sometimes the output is passed on to some downstream software components. So in this case, if you don't do some sanitization or some other checks, what you can end up having is this malicious piece of code or content basically passed over to those downstream pieces of software that might have permissions or accessibility beyond regular user, so elevated permissions, and that can really compromise the system. For example, if you use SQL injection that is passed on and can be executed by like a SQL engine kind of downstream. So yeah, I really encourage, if you're not familiar, to look through this list. Can give you a good lay of the land. So this brings me to AI red teams and their role in the fray. So the term comes from Navy war games, right? You would have simulated games. You'd have a team that would serve as the attackers, and then you have a team that would serve as the defenders. So the red team would be the attackers, and the defenders would be the blue team. Hence, the AI red teams, their goal is basically to check the defenses of the organization by all kinds of simulated attacks, and also, other things, code reviews and other type of things that they may. Red teams typically do simulated attacks. So they discover these vulnerabilities. They do assessment of what they find, the safety and the risk, and they also inform mitigation and policy. Typically, could be inside the organization, but also outside the organization. So they do a lot of prompt injection. There's also some data poisoning attacks that they can do, whereby some organizations fine-tune their LLMs, and they're basically exposed to some risk that the data that they use for this fine-tuning might be poisoned, that contains some misinformation, or might have errors or bugs that may affect the LLM application. So that's something that's to be mindful of. So those things should be carefully looked at. There's also bias, harmful content generation evaluation, and also, it's important to note that some of these LLMs, some of these models can process and ingest multimodal data, not only text, but also images, audio, video, and stuff like that. And so what happens is that the scope of this, of this thing is quite big, right? I think I talked yesterday with someone here about the thing where you can, you can put in a prompt injection in an image that is kind of not visible to the naked eye, but if an LLM processes it, can really compromise a system. That's just a few of the examples. So for this talk, I'll talk about jailbreaking, which is direct prompt injection. So the idea behind jailbreaking is that you want to find prompts that cause the LLM to output unsafe, inappropriate, and really harmful content, or really output in general. So things that would bypass the guardrails of the LLMs. So some examples would be, tell me how to write a malware, and how should I get a cut of my employees' tips, tying back to the examples of the New York City chatbot. So on the right-hand side, there is a paper that became very popular. It's an academic paper called Sorry Bench that I really recommend to read. It gives, it's a few academic teams that basically map some of the jailbreaking ecosystem in terms of trying to find, a taxonomy, what are the different categories that people use, as well as how these things affect multiple models. So they did try some of these jailbreaking attacks on multiple models, and they have a heat map that can describe like what model is sensitive to what type of attacks. So they have largely four category types. Hate speech, crimes and torts, things like inappropriate topics, and potentially unqualified advice. And then they have a bunch of like subcategories. So it's pretty like comprehensive, that paper. And so that's just gave a few examples here that are some examples that I give in this presentation that happen in the real world. So as a basic jailbreaking example that I'll go through would be in the realm of unqualified financial advice. So you can ask a question about the exchange rate of the US dollars to the Japanese yen, whether it's going to be, going to go up any day by the end of the month. So if I ask this question to a real world LLM, proprietary LLM out there, I get, trying a few times, I get three types of answers. One is no, which is actually a financial advice that I was looking for. And then I might get some refusals. So the middle one would be a refusal that's more like general purpose refusal without any additional explanation, just doesn't provide any predictions and forecasts. So I basically hit the LLM guardrails, right? And the same thing applies for the rightmost example, but in this case, it's a little bit of a different flavor of refusal where I get even some explanation because there is no access to real-time data, then it's not able to provide me what I need. So in general, this is a good example and illustrates the non-determinism of LLMs. You have the same exact prompt and you get different responses, right? So, and then going back to the AI red team, that's where they can use automation tools to kind of discover those jailbreaking prompts automatically. And so Python, this is a Python conference, Python plays an important role in that. And there are multiple common open source libraries that people use. Pirate is really strong from Microsoft, has a lot of different functionality, Garrick by NVIDIA. And there is also some companies that develop software for evals and that also have some functionality related to red teaming, like the Deep Team from Deep Eval. There's also PromptFoo that has similar offerings. So in general, red teaming is a specific case of eval. It's just that the goals are kind of flipped. But that's kind of, so there is a lot of like things you can use that are open source. So what would be basic like workflow for jailbreaking? You might start with a prompt database that you have collected, and then you might be able to transform that prompt, end up with some attack prompt that you're going to try with a target LLM, and then you're going to try to figure out whether your attack was successful, right? Even whether it was refused or whether there was some whether you got what you wanted, basically bypass the guardrails of the LLM. So this is again just for a basic single turn prompt attack. So how would you go about like estimating whether your attack was successful? There are different ways that people have looked into. One is the rule-based classifiers, right? You can actually look at string matching, like regular expression, things like that. So in the example I gave is I'm sorry, I can't, things like that. Those are some of the things people have used. There is also some machine learning classification that can be done. There is a method to use an LLM as a judge or even a human in the loop, something similar to active learning, if you're familiar, for those cases that are a little bit more difficult to determine. So, if the attack were successful, you may add this to your prompt database, but otherwise, you might be able to transform it and then try again. Maybe the transformation will break it. So what's this transformation? So the transformation, all these prompt transformations, they're very easy to accomplish, very easy to get variants of a given prompt from a SID, and it's very easy to automate it. So that's why people have used it quite a bit, and there are different examples where you can use translation, right? Translate a given prompt to different languages, hoping that the guardrails for a model in this other language might be weaker. You can do like rephrasing in a different style, literary, slang, things along those lines. You can do different, prompt encoding. You can do, add punctuation, add, special characters, emojis, Morse code encoding, everything, if you want to encode it in Klingon language, whatever you want to do. And then also like you can change the prompt of the tone, the tone of the prompt, or the tense. So a lot of different transformations that are available, also part of the open source libraries. So that brings us to the challenges when you're doing this attack stuff is that, on the one hand, you have the LLM's non-determinism, right? So you can try the same exact prompt and give you different outputs. On the other hand, you can use prompt transformation. So the whole overall space is pretty huge. So what's your strategy of like exploring this space, right? How do you do diversity? How do you do, create quite different prompts from one from another? And, what would be, if you have like a certain number N of prompts that you want to sample until you get a refusal and then you give up, would you use that a specific fixed number? Would you change it and things along those lines? All these things are important because those are questions of, cost and time are a function of this number N. So, so in this presentation, so there are different approaches what you can do. You can use optimization. There's a lot of different things people have done. One interesting approach is basically to use uncertainty to help you, assuming that you have some information about, some uncertain information, or maybe some sort of a confidence interval, I would say, but not quite, about whether the attack was successful or not. So what some strategies that you might use, if it's very highly successful, you might stop sampling, right, and just move on to the next prompt. If it's likely successful, you might go and transform the prompt and try again. Also, the mirror case applies for the refusal cases. And then if it's highly uncertain, you might want to keep sampling, or you might want to show to a human being for additional review. So how do you actually go about like obtaining this like uncertainty information? So that brings me to the idea of token probabilities in LLMs. So LLMs are basically the next token prediction machines, right? When you train, in the process of the training of an LLM, you actually hide certain tokens from the LLM, and the LLM is trying to guess what's the missing token, and that gets rewarded if the guess was correct, right? So it builds some probability score of what that token should be, and typically the next token that it guesses is the token that maximizes that probability, right? So the same thing happens in inference as well. Once the LLM model is deployed, you can, once you can ask a certain question, and the LLM would, spit out the tokens one by one. With each token typically maximize the probability. There are, different caveats, there are temperatures and other type of parameters, but by and large, that's the main point I want to convey on this slide. So as, simple example, if you ask the LLM what it thinks about Boston, it could say Boston is, and then, there could be like different next tokens, and the next token will be V because it has the topmost probability. So different APIs, both proprietary and open source, provide you the type of information, though it's not true for all models, right? So, but it is possible to do that. And so what you can do is you can ask an LLM a yes, no, or multiple question, and then you see what are the next token probabilities for the first token generated, right? So this is really simple code in Python that allows you to do that with OpenAI. Here you specify the top most probabilities as 5. I believe this specific thing gives you up to 20. So it's just like a small technicality. It gives you like the log probabilities because it's kind of easier in terms of numerical stability, but all you have to do is take e to the power of that and you just get the probabilities, right? So in our former example, right, if I ask that specific question, I get like those answers with the API, so I can see that no was indeed like very dominant in this case in terms of token probabilities, and then you have like the refusals as well. I mean, so here is quite an interesting example of why companies are not too happy to give you that information, because the guardrails kind of like try to block you from knowing a bunch of things, but then I can get like from the token probabilities, I can still get some information about my original question. So that's on its own, companies are more and more leery about providing this type of information. So how can we use this in our case? I mean, a very basic thing would be to use an LLM as a judge, different from the target LLM. And you can ask it a question. You can give it a prompt candidate and the response. And then you can ask whether this is a refusal, yes or no. So typically there will be other tokens in the answer, right? And so the question is, how do you represent the uncertainty given all these tokens that you have at your disposal or at your hand from the response of the target, from the LLM as a target? And also you're doing it multiple times. How do you combine the evidence from all these different answers? So in this case, there is one theory. I don't know if people are familiar with, who's familiar with Dumpster-Schaffer? Has ever seen it? No? Okay, right. So it's going to be new. So this is a Dumpster-Schaffer theory. It was invented in the 60s and 70s by Arthur Dumpster and Glenn Schaffer. The good advantage of that is that it allows you to represent epistemic uncertainty. So epistemic uncertainty is about lack of knowledge, right? As opposed to aleatoric uncertainty, which is things that you can't do anything about. So if you have lack of knowledge, you can get more samples. If you don't, if you have things like errors of sensors, there's nothing you can do to do better than, well, there are some other methodologies, but by and large, there's not a lot you can do. And the other thing is it has evidence combination rules. And so people have used this DST in multiple applications, in medical diagnosis, right, to do, combine different symptoms or test results in Internet of Things applications and robotics. So modeling uncertainty from like event flow of different sensors and trying to do sensor fusion with that, and even in cybersecurity for intrusion detection systems, trying to figure out how much uncertainty you have when you have the readings of those sensors, whether there was an intrusion in the system. So what are the basics of this Dumpster-Schaffer theory? I'm just going to specify for this presentation just a very bare minimum to understand. There's a little bit more that has to be included, and a lot of this is available online. So you have a set of possible outcomes. This is called the frame of discernment, denoted by theta. Then you have a power set of all of theta. This is all possible combination of the outcomes. That will be U. And then you have the notion of a belief probability assessment, a BPA, also called mass M, easier to denote M than BPA, like 1 letter versus 3. So this is defined over those members of U, and this is a very similar concept to the probability. They all, between 0 and 1, and they sum to 1 across all the members of U. And so the U members with like strictly non-zero BPAs are called focal elements. And so the Dumpster-Schaffer rule combination that we're going to see basically combines independent BPAs into a new combined BPA. So in our case, what would that look like? I mean, the frame of discernment would be S, the evidence that the prompt bypassed the guardrails or the attack was successful. So you have S and S naught. U would be the empty set, which will be a non-focal element. It will be will not really serve us a lot here, but we'll have the S naught, and then we have like a set of S and S naught at the same time, and that represents our combined uncertainty about the refusal, right, or about the success of the attack. So if you use the token probability generation, the next token probability for 2 different samples, you get 0.6. Yes, 0.3, no, 0.7 and 0.2, right? You can actually use the complement of 0.6 and 0.3 to get that S and S naught, right? And so that would be the BPA in this case. It's very easy to represent this in Python. And so what would be like an example of combining those things? So typically what you do is first you have like on the left-hand side some sort of a table, right? The table goes over all the non-focal elements, and from both the BPAs that you want to combine. And here in the third column, we would have the intersection. So you basically list all the focal elements, and the basic rule is that for each, you just do multiplication for the different columns, and then all these columns that you need to sum, you need to look at, you basically go on summation, right? So as an example is the notion of a conflict, which is denoted by K. So that would be where there is a disagreement between those VPAs. So that means that the intersection is the empty set. So that would correspond to the second and fourth rows. So you just multiply, you multiply the VPAs here and multiply them here, and then sum them, you get 0.33. So there is a normalization factor that will be applied when we do the combination, and that would be 1 over 1 minus k. So in our case, 1 minus k is 0.67, so they're all going to be divided by 0.67, right? And so we'll just take the first example of combining the first focal element for a successful attack. So again, like you're looking in the table where, we see S's, so that would be the first, third, and seventh column. You just add them up, and that's how you get, the combined evidence for the first, for the first focal element. And then you repeat the same thing for all your focal elements to get that basically evidence combination. So what I mentioned, I just like my presentations to be self-contained. This is the mathematical formulas that I've used in the example. And it is important to say that what makes the Dempster rule for evidence very attractive is that it's both commutative and associative. So it doesn't matter, what order you are doing this and what order you are adding and multiplying, you'll get the same result if you get the sequence of those evidence. So, I'll just do a little bit of comparison with another methodology that's used for combination of evidence, which is Bayesian probability. So in terms of the uncertainty model, right, you have the PPAs, whereas with the Bayesian, you have this single probability distribution that must sum to 1. The representation of ignorance, we don't have that really in Bayesian probability theory. You might argue that a uniform prior or posterior that would maximize the entropy would give you that, but I disagree. And then, we have you can explicitly represent the uncertainty as we showed you're using the Dempster-Schaffer. Prior probabilities, this is a pain for Bayesian. We don't have that problem for DST. And in terms of evidence combination, right, we use the base rule for Bayesian probability, and then we use we can use the Dempster rule of combination. There are, by the way, other rules later on. So some examples, possible examples, you could see, when one evidence is highly uncertain, the second one is 0.6, we can see that the combined evidence goes in the direction of the first one, which is something that you would expect. There's also some conflict of evidence. You can see that they are basically split between those two, between S and S naught, as one also might expect. So what are basically some limitations of this Dempster combination rule? So the problem is that if you could see the conflict, we divide everything, normalize everything by 1 minus the conflict, right? So if you have very extreme, high extreme conflict, it would be 1, and then this will break down, right? Division by 0. So there are other combination rules that allow you to work around that, and there's other things you can do, like weighing, even within the Dempster Schaffer, with the Dempster combination rule, there are some other things you may be able to do to have a workaround. Another thing to be mindful of is that U is the power set of theta, right? So if you have a large theta, you have, the computation becomes more expensive, so you can't really use it on huge frames of discernment. And then finally, the Dempster combination, the rule is basically assumes that you have independent BPAs. So that's another assumption to be mindful of. So just the big picture of or recap of or takeaways of what I wanted to say. The naive method, we just use, a fixed n, and we just try again over all the samples. If you use DST, you can do a more efficient exploration. You can stop immediately if you get more certain results, and if you have uncertain results, you can try to continue this exploration, transform more, and and do this type of thing. So on average, it will lead to a lower number of queries per discovered vulnerability. Oops. And the last slide before the questions is, there's a lot of things you can potentially do with this. You can combine evidence from multiple LLMs as a judge. There's alternative combination rules. Jaeger combination rule as an example, there's quite a bit of them. You can model different refusal levels, strong refusal, weak refusal. And you can also apply this to other type of attacks and in conjunction with other methodologies. Thank you very much for your attention. And maybe if you have some questions, I don't know what time it is. Yeah, we have a little time, I feel, so. Yeah.
So the DST that you presented, are you intending that to be used by like internal red teams that have those next token probabilities available to them, or is it like intended for external where like you can infer that by making a bunch of queries and sampling?
Yeah, no, it's a good point. I think because you have the choice of the LLM as a judge, you can decide what it is. It's not your target LLM. So you can use a bunch of like LLMs that do permit doing that, and then you do have a choice of that. So yeah.
Makes sense. And then also like, I'm just curious, do you think there's like much investment going on in like AI red teams inside of these AI companies? Because like in my experience, it's not that difficult to get it to like output things it's not supposed to.
Right, but you might want some more. I mean, there's been like, so I think this is like one subset of a lot of problems that AI has. I think there's like all the MCP security and all the question about like permissions for agents and all kinds of different things. So there is like quite a bit of like very large acquisitions of companies that operate in the field. So it seems like it's really a pain point. I mean, it's true that it's not that hard to come up with some examples. The question is like, how do you prioritize them? How do you like, what are things you are not aware of and things along those lines? So.
Because it just seems like you just stuff the context window with enough crap and it'll follow along eventually, right?
That's true, yeah.
So, I was just...
Okay. Yeah.
Is it still possible with DST guided that the output could say the model's okay, it's guardrailing, but could that be a false positive if the people just aren't prompting enough diverse?
Sure, yeah, it is. Okay. Well, thank you again.